You know, we're gonna have class time to work through, so like 8 through 17. So if you run into something that's confusing you, then we can discuss it. But it's all kind of now combining stuff like tangent lines and average rate of change into what we're doing now, which is like we can calculate derivatives. So quick clarification on this. This shouldn't be a huge mental leap for us because we've already discussed what this means. What is the meaning of this limit?
You're trying to find the derivative of the x to the fourth.
Very good. So this particular limit, this form of a limit, where you got a thing minus a thing over a thing, and then as this thing's approaching zero, this is a form that you recognize as this is equal to. Is everything okay back there?
I'm drinking all my water. So I have anxiety when I cough. So
Everybody is though.
You can go for a walk if you want to get the coughs out.
Just open the window.
Okay, so this, if we want to use this mathematical notation, we'd say this describes the derivative of, this is the derivative operator, so to speak, the derivative of, like Trey said, the x to the fourth function. Okay, so this limit and this derivative, I can use the equal sign, they're equivalent to each other. And then now we know there's a nice rule for taking the derivative of a function like this, you get 4x cubed. So it turns out that if you applied this would be a bit of a pain to do. You'd have to expand this. It wouldn't be like, it'd be like a good half a page of work. Yeah, it would be, you'd have to expand that out. You'd end up with a fourth degree polynomial, cancely-wancely, take a limit. You'd end up with this, long story short. But now that we know that form, it's very easy and direct to say, I recognize this is a derivative. That's the derivative I'm talking about. That's the answer. Okay, so that's all there is to it. This one's a little different.
It's the same, you're just trying to find out a specific value.
Yes, very good. So this is the derivative of a certain function evaluated at 7. So how do we write that? Because I don't want to write a whole sentence, right? A lot of math notation exists so that we don't have to write a bunch of sentences. I would say this is a symbol you may not have seen before. I doubt many of you have seen this. So you say it's here's a lot of people want to do this. This is wrong. You can see why, it's understandable why you might write this, but this is incorrect. Why?
That's not a function.
That would just be a 0.
Yeah.
Well, it's a flat function. I mean, you can think of it as a function if you want, but it would just be a flat line, so its derivative would be 0. So that's basically what's happening here is you're plugging the 7 in too early. So what you want to do, the way you notate this is you say it's the derivative of the square root function evaluated when x is 7. So this big bar here means evaluated at, or evaluated when. It's a very nice notation because if you guys get into multivariable calculus where you have x's and y's and z's and stuff, you could have a derivative that has multiple variables, and then down here you could say evaluate when x is this, y is this, z is this, etc. So it's a very nice, concise way of saying something. So then, nice and concise. So what you do is you'd say, okay, I know the derivative of root x. Again, remember guys, it's x to the 1/2, so that turns into 1/2 x to the negative 1/2, which is equivalent to 1 over 2 root x. That's a good one to know. The derivative of root x is 1 over 2 root x. So what I'm going to say here is this derivative, let's do it below, I guess, is 1 over 2 root x evaluated when x is 7. Almost. So that now we can actually evaluate it 1 over 2 root 7.
Would that be the limit?
Yeah, so this, notice the equal signs. This limit is actually equal to a number, which is a little bit different than this last one. This limit was actually equal to a function. So that's a distinction that you have to be able to make when you're looking at these. So sometimes the limit is describing, so basically this is, just to recap, this is saying the derivative of the function x to the fourth. And the answer to that is 4x to the third. Whereas this is saying, basically, what's the slope of the tangent line of the root x function when you're over here at 7? That's what it's asking. How steep is that tangent line over there at x equals 7? The answer to that is 1 over 2 root 7. Okay, any questions on that? There's 2 pages of those. They should be pretty straightforward. It shouldn't take you very long. But yeah, the first thing I'd recommend looking for is the answer going to be a function or is the answer going to be a number? Once you have that, once you're pretty confident that you know the distinction or which one it's going to be, then you proceed with doing your derivatives and stuff. So there was one last thing. Oh, okay. You'll notice that 20, 21, and 22 are just more piecewise functions. You do them the same way we talked about yesterday. You just take the derivatives and just be really careful about what's happening with the slopes at those junctions. So if you have a function and the slope changes rapidly or instantaneously from say 2 to 1, that's a sharp turn. But if the slope smoothly transitions from say a slope of 2 to a slope of 2, then it's differentiable there. Like you could theoretically have, or actually in practice you could have a piecewise function that goes parabola and then changes into a linear like that. As long as you have it set just right, so just for example, if it was something like x squared and this was 2x, and you just have it switch at 1. Small problem, I gotta throw -1. This function, think about the derivative, this is f, the derivative would be 2x and 2. And so you can see the slope here where it transitions is 2 and 2. Does that make sense? So this function would be continuous and differentiable everywhere. That's the only way you can make that work, is if you have a nice transition from where the slopes are equal at that x value. Anyway, if you run into issues on those, we can of course discuss them. But okay, last thing. I just very briefly talked about vertical tangent lines yesterday, so let's just make sure there's no confusion. So take a look at 23. I'm going to list here all the ways that you can have that you can be non-differential. How can you be non-differentiable? Great. So a hole. Anyone else? Jump. Vertical asymptote. You can write the whole word out.
Whoa.
Wow.
Dedication to our education.
So dedicated. So pointy. By the way, this is a whole family of stuff. Really, any discontinuity. Holes, jumps, asymptotes, right? But then there's another family of places that you can be non-differentiable. There's a pointy spot. And the other one we're going to add in is vertical tangent line. And I'll give you a very concrete example of that right here. It's the cube root function. So 23b, 23a is a very obvious spot. Where is 23a non-differentiable? At 0. So this question says find the derivative. So let's just clarify. 23a is very simple because you just say, well, g is 1 over x squared. The derivative would be -2 over x cubed. And we can see pretty clearly that where does this guy not exist? 0. Where does this guy not exist? 0. So where does the derivative not exist? 0. Okay. And then the reason, so this guy is, it's an undefined at x equals 0. Okay, so that one's not too tricky to visualize, right? Because the original graph, you can see, oh yeah, the derivative is not going to exist at that vertical asymptote. But b is a cube root, which looks like this. And it would not be unreasonable for a person to look at that and go, oh yeah, he's smooth, there's no pointies, he looks fine, right? There's not going to be any non-differentiable spots. But watch what happens if you take the derivative. This one's a little tricky, right? So you got, you have x to the 1/3 power. Let's go over the margin here. So is that where you got most of you guys, I'm assuming, are at that point still, where if it's like an integer power, if it's like x to the 5th, it's really easy, but if it's like a fraction power, it's still a little. Okay, so I'd recommend just rewriting that root as a fraction power, and then same rule. So you use the 1/3 down here, subtract 1 from the exponent, you get negative. So that's negative 2/3 power. So there's your derivative. Can I rewrite that? Yeah, it's 1 over, this 3's on bottom, 3 times is it cube root of x squared or square root of x cubed? Cube root of x squared, very good. So cube root of x squared, there we go. That's a little 3, by the way. 3. Someone say, question? No? Now, look at that. Now it's a bit more obvious, right? Evidently, x can't be 0. So this derivative is undefined when x is 0. Which raises the question, well, why? It's clearly, well, I shouldn't say clearly, it's not obviously not a pointy, but it's, if you examine this thing, say look at Desmos and zoom in, you'll see there's not really a pointy spot. The thing that's happening here is that the tangent line, if you drew a tangent line, it would be vertical. Like we talked about yesterday, the slope of a vertical line is undefined. So since the derivative is the slope, and the slope is undefined, then the derivative is undefined, so it doesn't exist there. Does that make sense to everyone? Are we okay with that? Okay. All right, that's pretty much it. So the rest of those on that page are things like, I don't know, like the next, what's 23C? What shape is that? Birdie. Birdie, pointy. Yes. And you'll see that bear out when you take the derivative. You'll say, oh yeah, because it doesn't exist when x is 0. You can see algebraically that x can't be 0 on the derivative. So
Are most of these 0? Are most of these 0?
Most of them, yeah, but it's the thing is why. So like you're gonna find on D, if you do if you graph D correctly, you'll find that D is non-differentiable due to a vertical tangent line, whereas E is non-differentiable due to a vertical asymptote. What is F going to be non-differentiable due to? You might, yeah, a jump, exactly. So they all, and then how about G? What's G non-differentiable due to? Pointy. I'm going to leave that as a little challenging one for you. We may have actually briefly touched on that, but actually taking the derivative of y equals absolute value of x, there's no like quick and easy algebraic method, but if you just think about what that graph looks like, you'll figure out, oh, I can write a function, a piecewise function that gives you the derivative. And then, okay, anyway. Same thing, 24 is the same thing. A few of them have pointies, a few of them have vertical asymptotes, a few of them have vertical tangent lines. So, all right, I kept it under 15 minutes. Wow. You know, they used to say, pat yourself on the back. I always took that literally. Every time they said, give yourself a pat on the back, I would always physically do that.
I think that was